am pushing record. It's working. We're good. All right. And online, can see okay. So, when I think about the ACT, there are things that are the meat and potatoes all the time. It's always going to be there. ACT. There's always going to be stuff with percents. There's always going to be stuff with ratios. There's always going to be lots and lots of geometry. But what we are doing today is not necessarily the meat and potatoes. These ones are the ones that they like to throw in as curveballs. I have seen an entire ACT test with nothing about imaginary numbers, and then they kind of get on a roll and maybe you'll have 3 questions with imaginary numbers on it. I've seen many tests that have nothing to do with logarithms on them at all, but sometimes there'll be 2 or 3 questions about logarithms. And so these ones are not guaranteed to be on the test, but one of these categories will definitely show up. It just kind of depends on what rotation they've decided to do that they show up. So the first question, I just said imaginary numbers. What is the definition of I? It is imaginary, but what is it? What's the equivalent expression that we can also, if they say I, close to -1, it is the square root of -1, which is what makes it imaginary. There doesn't exist a real number that if you multiply it by itself, it multiplies to -1. In fact, there doesn't exist a real number that you multiply by itself that it equals negative anything. But this I equal to -1 allows us to just kind of set the fact that it doesn't really exist in the number sense that we know it and still work with it. And interestingly enough, later on in physics, they discovered it's not quite imaginary as they think. It's a bad name for it, but it's already grandfathered in. So what we can do is use this I to say, okay, we can break this up into the square root of -1 times the square root of 49. We can split those 2 portions, and so we can always just pull out the negative sign as its own piece, and that becomes I. Square root of -1 is I. So we have I, and what's the square root of 49? 7. And so the square root of -49 is 7I. And then the same way here, again, we can pull out the negative as I. It's the square root of -1. The 28 can break up into 4 and 7. And so square root of 4, nice, pretty, perfect square, 2. Square root of 7 is still square root of 7. And so this is 2I. Square root of 7 is left behind in the radical. And so when we're simplifying these radicals, it's about what can escape, what can't. But anytime you have a negative inside your square root, it just can be rewritten as I. So I has this interesting property that if we have just I, it's this square root of -1. What would I, marker's not writing well, I squared equal? -1. It's that undo, that reverse. And so I squared is -1. Well, okay, what about I to the 3rd? That's going to be I squared times I, because there's 3 of them, right? I squared, we already talked about, was -1, and so this will equal -1 times I, or just -I. And then finally, well, what about I to the 4th? Well, this is I squared times I squared. And we already said, well, this is -1 and -1. What's -1 times -1? +1. And then if we go beyond that, I to the 5th, that's going to be I to the 4th times I. 1 times I. And it goes right back up to this. And so I think of it as a clock. It starts at 1. If we have anything to the 0 power, the 4th power, the 8th power, 12th power, any multiple of 4, it's going to go to 1. If we have 1 or 5, or 8 plus 1 is 9, 12 plus 1 is 13, we have just I. If we have it to a squared power that's not this, for instance, to the 2nd power, I squared, to the 6th power, I to the 4th times I squared, it goes to -1, and then -I, that's I to the 3rd, I to the 7th, I to the, what would it be, 11th. And so it just circles around one of those 4 for any power of I. There's 2 different ways to deal with these problems right here, which is what that idea is leading up to. The first question is this an even or an odd power for this first one? Even. And so we could rewrite this. I'm going to change colors so it's a little bit easier to see. This is I squared to the half of that. What's 894 divided in half? 197. 197? Oh, 497?
447. 447.
447? Okay, that looks right. So, again, what was I squared? If I is just the square root of -1, I squared is going to be -1. What's -1 to an odd power? -1. Here we have, again, an even number. So again, we're going to break this into I squared to half of this. This is 140. It's a little bit easier to do in your head. And again, I squared is -1. What's -1 to an even power? All those negatives get paired up, canceled out. It becomes just +1. Odds are a little bit trickier. We know it's odd, but is it odd in the equaling I sense or equaling negative I sense? And so the easiest way to do this is to split off 1. This is I to the 998 times 1 I left. So 998, again, we're going to be rewriting this as I squared to an even number. So half of 998, half of 1,000 would be 500. 1 less than that, we have 499. I squared, again, is our -1. -1 to an odd number is negative, and so this answer is -I. If we split it off here, we're going to have 360, and then one I off to the side. I'm running out of room, so I'm gonna break this down. We have I squared, half of 360 is 180. I squared is -1. To an even number is just 1. And so positive I would be our answer. So here, it'll be 1 if you have 2 evens in a row, because everything gets canceled out. Here, it's -1 if you had an even, and then it went odd, so now it's -1. When you've got odd numbers, you split off one I, and then see what's happening with the other numbers that are left over. Bit of a shortcut, and it has to do with this cyclical nature. If you divide 894 by 4, calculator's fine, what do you get? So the 0.5 remainder, the answer is going to be -1. And it doesn't matter what number you've got. Because there's 0.5, there's essentially I squared is left over. It's always going to be the -1. How about this one? If you take 240 and you divide by 4.
Or 280?
Oh, 280, thank you. I miss
70.
70. Nice whole number. If it's 0.0, if there's no decimal left over, that is the 1. It finished the complete cycle and just ended up back at 1. How about the 999? What's 999 divided by 4?
249.75.
So 0.75, that's 3/4 of the way. It almost made it to a complete loop back to 1, but it didn't quite, and that's our -I. If you divide the 361 by 4, you'll end up with 0.25, or 1/4. And so this is conceptually what's going on. That one's a bit of a shortcut if you already understand what's going on. If you can't remember that circle, that's when I go back to this of, okay, what does it mean? We're looking at to what power? Because there's going to be all of this that just turns into a 1, and then we're looking at the leftovers. What else is there? All right. So, the second topic that I wanted to talk about today, this one I can guarantee is on the test. It shows up in some form all the time, but you talked about it in Algebra 1, and then you really talked about it in Algebra 2. What happens with the difference of squares? Here we have 2x squared minus 8. If I tell you it's a difference of squares problem, what is the first thing that we're going to do? Trying to factor this. Okay, we're going to take a step back and look at this one then. So, here we've got a fraction, it's multiplying, it's got the I involved, and we're going to talk about that. But, essentially, on this top part, we're multiplying it by 1. Does anything really change? No. And so this is just 1 minus I. But, down here on the bottom, what happens is FOIL, first, outside, inside, last. Our firsts ends up with 1 times 1, or 1 squared. Our outsides are 1 times -I, which just gives us -I. our insides are 1 times I, which gives us positive I, and then our lasts, I times negative I becomes minus I squared. The difference of squares is about this phenomenon in the middle, where that outside-inside thing are the exact opposite of each other and they disappear. And so we end up with 1 squared minus I squared. These plus minus disappeared. And so we have 1 minus I over 1 squared is just 1. And then minus I squared is negative 1. What happens when we have minus negative? Turns into positive, and so we have 1 minus I over 2. And I'll erase some of this stuff. Oh, sorry. All right, so based off the faces you gave me, we're going to take a step back. If I have x squared minus 49, do you remember factoring that? Okay, so the difference of squares tells us we've got subtraction right here. X squared is a perfect square. 49 is a perfect square, and so we could look at this as x squared minus 7 squared. And this factors into two numbers that multiply to 49, 7 and 7, and they differ by 0, or they add up to 0. And so we have x minus 7 and x plus 7. The reasoning behind this is if we multiply this out, or if we FOIL this out, we would get x times x gives us the x squared, but our outsides would be 7x, and our insides would be negative 7x. And so those middle terms cancel each other out, leaving just negative 7 times 7 gives us the negative 49. And so that is the difference of squares. And where that comes into play, I'm going to copy this problem up a little bit higher. We have 2x squared minus 8. First thing with factoring is to always take out the greatest common factor, to always remove the number they have in common. So what is the common factor between our two pieces or our two terms? 2. So we can bring 2 out, and we're left with x squared minus 4. X squared and 4 are both perfect squares. And so what would this piece factor to?
X minus 2, x plus 2.
Yeah, so the 2 hangs out, x minus 2, x plus 2. The place where this takes on a level of difficulty or a level of trickiness is that it's always not going to be as obvious as this or this. As you can see, the 2 factor kind of hid that there were perfect squares, because 8's not a perfect square, but by factoring out the 2 first, then we got to perfect squares. Here, with x to the 6th minus y to the 8th, the thing that I want you to be comfortable with is the idea of being able to rewrite numbers to something that is equal to them while keeping the same problem. And I did that a little bit with the I, when we turned it from I to I squared to a different power. This x to the 6th is the same as x to the 3rd squared. You remember those exponent rules that we power to a power, we multiply, we can undo that. We can break that number down and turn this into a power to a power. In the same way, y to the 8th is y to the 4th squared. And so now, this is still a difference of squares problem. Following the pattern, we're going to have x to the 3rd minus y to the 4th and x to the 3rd plus y to the 4th. And so being able to change the look of it and then use the rule, one of the useful tools of algebra. Even if it doesn't instantaneously look like the rule that we learned at the first time, we can massage it, tweak it, make it fit the situation we've got. Timing-wise, we're doing good. So I'm going to move this a to the 16th minus 16 up here. So, again, we can tweak this a little bit. A to the 16th can be written as a to the 8th squared. And the 16 is 4 squared. What would be our factored form of this?
Would it be a to the 8th minus 4, a to the 8th plus 4?
They are going to serve you this answer in their multiple choice silver platter, and it's going to be wrong. Remember that ACT is all about, are you in on the joke? Are you showing off what you know? This is the correct process, but it's not finished. We're not done. What do you notice about either of these two pieces? Yeah, this is still a difference of squares. You've got to keep going. This a to the 8th becomes a to the 4th squared, and this 4 becomes 2 squared. And so this piece we stop. We say, yeah, we can't factor that anymore. And so this hangs out, but this becomes a to the 4th minus 2, a to the 4th plus 2, and then the a to the 8th plus 4 hangs out. And here, a to the 4th, we could keep going, but our number isn't a perfect square anymore, and so we stop there. It doesn't factor as a perfect square. If for some reason we had started with 64, we actually could have kept going. We could have kept splitting off. All right. So our final problem ties these two ideas together, which is why I gave it in this particular order. This one is a problem 58 from a particular test. So definitely one of those challenge problems near the end. And it says, what is an equivalent expression to this expression? And we just talked about the difference of squares, that whole, they have to be minus so we can turn into 1 plus, 1 minus. But if we consider that I, we can write this as 49 y squared minus negative 81. square root of 49 is going to be 7. Square root of y squared is going to be y, and so our first term is 7y. That's our first square, or our first thing. And our second square root of negative 81 is, square root of 81 is 9. Square root of the negative is I. And so it's not something that we use a whole lot. It's not a real factor. It's not a real answer. And so we don't deal with this when we talk about factoring, but it is technically equivalent to turn this into 7y minus 9i, 7y plus 9i. So again, of all the tests I've looked at, I've seen this once. But it is a possibility. It's combining the idea of what does negative I, or what does I mean? What would the equivalent expression be? And if we multiplied this out, these would cancel with these, so those center terms would go away, same as difference of squares, and then negative 9i times positive 9i would be minus negative 81, or turn into plus 81. So, again, that is the outer limits of difficulty, but it's worth mentioning, and it combines our imaginary numbers and our difference of squares very well. So, again, as I prep for these, I take a lot of the same practice tests you do, I just do it in large quantities. I don't get every problem right. I have been known to do stupid mistakes, I've been known to drop negative signs, but usually when I go to the answers and I check myself, I can say, oh yeah, that's where I messed up. 2 times that has not worked out. One of them, the ACT was wrong, and I went on a teacher forum to double check with them of, yes, is this something that they should not have done? Mistakes can happen. If you run into a mistake on the test, give it your best guess, but do not let it kill your time. It's just not worth it. And if enough people complain about the problem or say, hey, I want you to double check this problem, they have been known to throw things out because there was an error. The second one was one that I was taught wrong in my high school experience. And so that also happens. So if we consider the number 5, we want to list all of the number sets or the categories that this number 5 belongs to. So, off the top of your head, what's one group you can think of?
1 5. 1 5.
1 5? No, like sets like integers, whole numbers.
Oh,
What number categories does this fit in?
odds.
Odds? Okay. But no, it is a natural number. So natural number is those counting numbers. Those are the things that we very first started off with. 1, 2, 3, up to 1,000,000 and past. Those counting numbers are the natural numbers. What other number sets have you worked with?
It's a rational number.
It's rational. Excellent. Rational means that it can be written as a fraction, and so frequently when we think of rational numbers, we think of fractions, but 5 can be written as 5 over 1. Other numbers it belongs to, other number sets it belongs to.
Integer.
It's an integer. Excellent. Integers are both the negative and positive counting numbers, so it is an integer.
Is there a category real number?
Yes. Real numbers is bigger than rational because it also includes irrational. Things like pi or the square root of 2. Those are still real numbers, but we can't really quantify them. And so those are the irrational ones, but all of them are real. And so because 5 is a real number, yeah. Whole number is one that it falls into. I don't know that people talk about that one as much. The whole numbers are kind of a funny set. They're the counting numbers plus 0. And so it also belongs to that set. All of this I knew. The one that I got wrong is that I said it wasn't a complex number. And so complex numbers is anything that can be written as A plus B times I. And so it has a combination of A being a real number and this piece being some multiple of an imaginary number. Complex number system combines both those real numbers and the imaginary numbers. And so for me, 5 does not look complex. It looks pretty simple, right? I thought complex had to be in this form. And it can, because it's 5 plus 0 I. As simple as 5 feels, technically it is a complex number. It fits in within the complex number system. It's just a really basic one. Just like it's a rational number, even though it's just written over 1, it is also a complex number. It just has 0 imaginary parts to it. And again, that's one that I was taught wrong. I thought complex had to have both of those. I didn't think about it as the subset. That one is one that I have seen on 3 different practice tests. And so there is a real possibility that it shows up and says, which categories does this number belong to? And it's one of those set 1 only, set 1 and 2 and 3. And so you have to have that combination of things. But I just want you to be aware, because that is a problem that I've seen, and that is a problem I personally messed up on, that it is a complex number. All right. Pacing, am I going too fast? Is there anything you'd like to go into more detail with that? Okay. The second set of problems that I wanted to deal with you guys is the idea of exponents and logarithms. And exponents and logarithms are the mirror image or the reverse of each other, kind of like square and square root. And so the first thing that I need to just know from you guys and online as well, have you seen logs before? Have you worked with them yet? Yes there, no there, yes there. Online? I got a thumbs up. So, logarithm is the most basic. If I have some number x to the nth power is equal to b. We're using a bunch of variables here. The way to rewrite it says the log of this bottom number, the base of this number, is equal to what the exponent was. And so if I have 2 to the x power equals 8, the log, this was the base goes to the bottom. The log base 2 of 8 is equal to x. And so that is the fundamental thing of what does logarithm mean. So, one of the most simple questions says, if I have the log base 5 of 5 to the 13 over 2. These two cancel each other out. It's one of those nice, amazing things with logarithms. If I have 5 and 5, well, let's say that this equals x. if we go from logarithm back to exponent, it's going to be 5 13/2 equals 5 to the x. And so these equal each other. So, using that rewrite between log and exponent, can you rewrite this as an exponent problem rather than a log problem? Can you change the writing style? Again, this is read as log base x of 36 equals 2. So, the reason I reiterate how to read it or how to say it, log base x, base goes on the bottom. And so this will be x to the second power is equal to 36. So, of our options 4, 6, 8, 16, and 18, which one is going to be our value for x? 6. And so even if you haven't seen logs or haven't worked with them a whole lot, it is very approachable on about half of the problems you see. And so even if it's something that's not very familiar, if you understand the basics of what it means to be a logarithm, you're still able to find an answer that makes sense. So, I'm going to take a break from the logarithms and circle back to exponents, and then we'll catch up with logarithms again in a few minutes. And that's kind of the trade-off that I have to make. So, are you confident with dealing with about this level of complexity for exponent simplification, reduction, combination, that sort of thing? So, within this problem, we've got all of these transformations or these changes going on. So, when you multiply polynomials, what do? If I have a squared times a to the 6th, what will it equal?
8
a to the 8th. When we multiply, we add the exponents. When we divide, if I have b to the 4th over b to the 3rd, what do?
Subtract.
We subtract the exponents. When we have power to power, if I have x to the 3rd to the 4th, this is one that we brushed on with that different stuff.
Multiply.
We multiply. When we have a root, if I have the 3rd root of, I don't know why, I'm running out of variables, what do we do with that one? We divide. If we have power, we were multiplying, so if we have a root, we are dividing, and this becomes y to the 1/3. If this had been y to the 4th, it would have been to the 4/3. But the root divides that exponent. And then the negative, really it's a specialized case of divide. It's a formalization of that divide. And so if we have, I don't know, k to the -5th, this moves it to the bottom and it becomes k to the 1/5, or k to the 1/5. And so negative, it's just like division, we're subtracting the exponents, but if you subtract from nothing, you get negative exponents and it becomes in the bottom of that fraction. And then to the 0 power, I forgot that one. What's a 0 power?
1.
So, in this, how many things does this 4th power apply to? Everything in the parentheses. So we have 2 to the 4th, we have a to the -1 to the 4th, which is -4, and this b is to the 1/2 because it's a root, and then we again multiply by 4 halves simplifies down to 2. If you need to write more intermediate steps as you solve it, that is absolutely okay. It's a balancing act between what your brain does and what you write down. So that does our first step. When we do any of these rules, what has to be true? What do they need to have? Here I had a to the 2nd and a to the 6th. If it was a to the 2nd and b to the 6th, what happens here? We just leave it alone. They have to have that common base before you can do anything. And so even though this is one problem, in reality, it's 3 mini problems. It's 3 situations. We're going to say, okay, my number is just my number. There's no other numbers to combine it with. This is 2 to the 4th power. That's part of my final answer. But I have a down here on the bottom, and I have a to the -4th up on the top. Negatives are the ones that move. And so all 4 of these are going to move down to the bottom. There was already 1. Now there's 4 more. In the bottom of our fraction, we're going to have a to the 5th power. And then finally, we look at our b. We have -3 down here. We have +2 up top. Negatives are the ones that move. So this moves up to the top. We already had b to the second power, now we have 3 or more of them, so we have b to the 5th power as well.
Can you go over b to the second? Like,
Oh, how I got that?
yeah.
Okay, absolutely. Thank you for asking. So, b to the negative third, I'm going to do it just as a b problem here and leave all the other stuff out because it's a little bit... Because it is to the negative third, negatives are going to flip-flop the side of the fraction. And my notes are bad. That's my fault. That should have been 1 over. Bad handwriting, I apologize. So, this b to the negative third moves up into the top as b to the third. Every time it changes above or below the fraction, it's changing the sign. And that's...
I was asking about how you got like the original b to the second, like how you went from square root of.
Okay, so, let's rewrite this. We have the square root of b to the 4th, right? Square root is b to the 1/2 power. And so 1/2 to the 4th is 4 times 1/2. 4 times 1/2 is where I got the 2.
Okay, thank you.
No, I'm thrilled. Somebody stopped me. In my class, that's worth extra credit points. Anybody who's willing to speak up and say, slow down, you are too hand-wavy. So, yes, that's where that one came from. Roots are fractions. Fractions, it just happened to multiply out. All right. So, the reason that I took the time to write out these rules is because the log rules are very, very similar, but they're used less. They're taught for the logarithm lesson and then kind of left alone, and so they don't stick as well. And so our first log rule says if I have the log of a times b, and for the clearness of notes, from this point forward, we're going to be talking about common log, which means we don't have to write anything down here. It's log base 10. Works for everything, but it's a little bit clearer if we aren't always having to put that little letter down there. So if we have multiplication, what did we say that multiplication turned into? Yeah, and so if you have the log of a times b, it's going to equal the log of a plus the log of b. Just like exponents, multiplication turned into addition, if we have the log of a product, it's going to be the sum of the two pieces. Same way, if we have the log of division, what do you think it's going to turn into?
Subtraction.
Subtraction. And so it's the log of a minus the log of b. How about power? What did power turn into power turned into multiply. And so if you have the log of something to the power, it turns into multiplication. This is going to pull down in front of the log, and it becomes k times the log of x. not really familiar with a root problem. I don't see logs of roots very often, so we're not going to focus on that one too much. And the negatives don't come up as much because, again, because of exponents, logs of negatives frequently will result in undefined. But the log of 1 equals 0. Because anything to the 0 power, remember we're looking at something to the power of 0, would equal 1. And so the log of 1 is always 0. So that's the reverse of this one. The problem that I wanted to talk about with that, I'm going to erase this one. Again, this is a problem that I have seen some variation of. It's obviously not always the exact same problem, but it's the same structure. I've seen the variation of it about 2 or 3 times on all the tests I've done. But it says that if log base A of x equals s and log base A of y equals t, then what does log base A of xy squared equal? So, very much a conceptual problem. There's no numbers. It's not calculator possible. It's very much the theory and understanding what can these numbers do. So, first question, which one of these rules does it look like we're going to be using? Multiplication and we also have to use that power because we've got an exponent. And just like solving, we want to peel off the layers first. We need to deal with this too before we can talk about the multiplication. And so with the power, all we have to do is bring it down out front. This 2 is going to come out front, and this becomes 2 log base A of xy. And so with these exponents, we can bring the power down to the front. Next, with the multiplication, we can break this into the log of x and the log of y. And so we have 2 times log A x plus log A y. And again, our rules tell us if we've got multiplication, we can break it up into the sum of the logs of the pieces. Then finally, we're just substituting in the stuff they told us. They told us that the log base A of x was s, so we replace it with s. They told us the log base A of y equals t, log base A of y, t. And then both of these things are still multiplied by 2. So, again, if it comes down to studying geometry or this, your time's better spent on the geometry. But if you're feeling rock solid on geometry and you are aiming for perfection or really, really close to it, this is the type of stuff that you'll do to fill in your gaps of knowledge and make sure that you've got all the pieces rock solid. Especially if you have not yet learned logarithms in school, the thing that I can tell you and really emphasize, and then even if you're doing it in school, it makes it so much easier. This rule, lots of people get. They make it, they understand it, all is good. If you can tie that in your brain to the log law, it becomes so much easier to learn. We added the exponents, we're adding the logarithms. We had multiplication, it turned into adding. And so the more you can lock that into your brain, the easier it becomes to use those rules. Because otherwise, in school, it's something that you learn for a chapter, and then it just doesn't get used as much. Logarithms are immensely useful, particularly in science. They are a way of talking about things that just have exponential growth, and so they're really hard to understand. If you've ever heard of a Richter scale for earthquakes, they're on logarithms. The idea that a 6 on the Richter scale versus a 7 on the Richter scale, the 7 was 10 times bigger than the 6. It shook the earth 10 times as much. And so they become ways of talking about huge phenomena. But mathematically, we teach them for the chapter and then they kind of disappear into the background. So that is that. We've got just a few minutes left. I don't think I'm comfortable diving into our last topic. I'll just tell Manoj we punted to the next lesson. So is there anything you would like to have one more practice problem with, or something that you'd like to go over? Do you want more of those simplifying the exponential problems? I've got those, so. I only threw one at you, so. Right. If I have g squared square root g to the 5th times h squared 4th root h squared 4th root h to the 5th, you can simplify that, or you can find the product of questions on any of those? Where did you get the? To me, this one was the trickiest, but,
Yeah, how do you get a?
Yeah.
okay.
Yeah, that's where I'm wondering.
So, this is the square root of g, correct? So, this is g to the 1/2. You can turn this into g to the 2/4, and that allows you to combine these two roots. So now this is part of the 4th root, it's g squared to the 4th root. So that one is kind of a tricky one. I had forgotten that it was on my list, so once I wrote it down, it's like, oh yeah, we should talk about that one. Again, being confident with turning things into other exponents and breaking them apart rather than just multiplying them together, that one would be a really good skill to practice. And so going from 9 to 3 squared so that these are the same and we can set these equal to each other, that's one of those skills that I would encourage you to get really comfortable with. All right. Once again, I'm going to be back in 2 weeks, I think. Manoj and Rakav will be here next week. But if you have questions over homework or anything else, it is always encouraged to ask. So snap a picture, send it in the chat is the easiest way, but otherwise we'll make it work. And that doesn't just hold for on these lessons. If you're midweek and you're just curious, if you send it to chat, I'll respond to it. So that's where things stand. Do your homework. Practice is the best learning thing there is. All right, we'll take a 5-minute break and then you are meeting with Lily again.